Alright, so I'm going to go above and beyond in my explanations for these examples in order to prepare us for limits, continuity, and then derivatives, and then integrals. So we're just going to be doing an overview of functions and highlighting all of the most critical details for the topics moving forward. Here we have example 1, and example 1 is asking us to find the domain of the function. As you should know, and you should know really well, the domain is the set of x values that are able to satisfy this particular given function. The function that we're dealing with is the function 1 over x. 1 over x is also known as the reciprocal function, and sometimes it's known as a rational function. So we can kind of throw those words in there just as a reminder if we're going to take some good notes. Not the end of the world if you can name it off the top of your head, but it also can hurt, and it sometimes helps you remember other details if you can give it a name. So the reciprocal function is also an example of a very simple rational function. As you know, rational is highlighting the word ratio, right? Ratio or a, cut that off a little bit. Ratio or a proportion, fraction, whatever way you want to think of it. So here the graph was actually already provided for you. Very, very generous of the example here. I'm going to highlight a little bit more there. Alright, so one thing I have drawn in, something from Algebra 2, something from Pre-Calculus, is this vertical asymptote at x equals 0. The equation of any vertical line is x equals something because every x value is the exact same number on a vertical line. So for example, the ordered pair is 0, 0, 0, 1, 0, 2. 0, negative 1, 0, negative 2. What do they all have in common? X is equal to 0. So here we have a vertical asymptote, this dotted line, sort of there as a guide in helping us draw this. Sometimes we say, oh, you'll never cross an asymptote. Well, that's not entirely true. While you'll never cross a vertical asymptote in a function like this, you can cross a horizontal asymptote. A vertical asymptote is a very, very strict restriction on your domain. Alright, so if you look over here, our domain, we're dealing with the x value. So what x value is completely off limits? You're dealing with a rational expression. X 100% in this case cannot equal 0. You are not allowed to divide by 0. But that doesn't mean x can't equal 0 in every rational function. Really what it comes down to is it comes down to the fact that you are not allowed to divide by 0. So basically I'm going to make a note of that. Not allowed, that's really the reasoning behind it, to divide by 0. And then our symbol for the word therefore is 3 dots in a triangle. So therefore, denominator is not allowed to equal 0. And you really are solving for what x cannot equal. So in this case, you'll just be like, all right, well, done. X cannot equal 0. That's it. Some books or worksheets or teachers, they're going to accept that as your domain. X can't equal 0, basically saying everything else is good. Someone like me, on the other hand, would like you to write your domain as more of, let's focus on the good, not the bad, and let's use interval notation to list everything that x can be equal to. Down over here, this is where x is going out toward and approaching the value of negative infinity. This blue is kind of showing us going in this direction. Alright, out here, this is us showing x going out toward positive infinity. So everything down here is good. I'm going to have graph. This branch is going to continue. We're good, we're good, we're good. As we come over here, we're just going to get really, really close to this orange dotted line here, this vertical asymptote. But it will never touch it. It will never equal 0. The more you zoom in, the closer you can get, but it's just going to go on forever. The same behavior is going to happen up here, flipped up into quadrant 1. This was quadrant 3. Same exact behavior, sort of reflected over, and continue on to there. So our interval notation, you always use parentheses against your infinity or your negative infinity. For domain, we always go left to right. When you describe increasing and decreasing intervals, you go left to right. When we describe concavity, concave up or concave down, we go left to right. The only thing that we go from bottom to top, the only thing we go from bottom to top is range. Everything else we're moving from left to right. Okay? So let's all keep that in mind. Green, I did just label what we called the horizontal asymptote in Algebra 2 or in Pre-Calculus. So we have a horizontal asymptote here at the line y equals 0. Y equals 0 is the x-axis, x equals 0 is the y-axis. Now a horizontal asymptote might change up. Next time it might be a slant asymptote. Maybe we'll have a quadratic asymptote or a cubic asymptote. Really, the possibilities are endless. This is more describing what we call our end behavior, what happens in really extreme scenarios. If you notice, I intentionally didn't draw it here in the middle. a horizontal asymptote sometimes is a little overused, and they're thrown out there quite too often. Really, on the right, I am approaching this value of 0, and we will get into that more. I might even talk about it in a second just on this one. And out here, I'm also approaching 0. So it's pretty good because it's approaching the same value on both sides, so I don't mind this one as much. Even when we did horizontal asymptotes in algebra, we often discuss when x approaches infinity. And this is where you might have first been introduced to something called the limit. So we said, what is the limit? The limit being, what number does the y value, the output, approach? What is the limit as x approaches infinity of this function? Algebraically, if you just look at it and reason it out, as x gets bigger and bigger, 1 over 1, 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000, as this bottom number gets bigger and bigger and bigger, the value of y, the fraction, the entire output, is going to get closer and closer to 0. The same will happen here. I'll be plugging in -1, -10, -1,000. And that's really where this horizontal asymptote comes from. It's not about what's going on here so much as what's going on out here. Now, this has it typed out this way. I would use this union symbol in between, those two parentheses right there, parentheses against the zeros, because 0 is not included. If 0 were included, you would use a square bracket. So the answer to this example is right over here. From -infinity until 0, not included, and then starting up again after 0 and continuing until x hits infinity or approaches infinity. All right, next example is this one over here. And this example is also asking for a domain. So kind of we start all this up. It's asking for domain again. And the domain is being requested of this radical. Okay, it's a square root. F of x is equal to the square root function, square root of 2x plus 3. This doesn't require a lot of overthinking, just like this one. If you wanted to only do it algebraically and not think of it graphically, fine. You say your denominator is not allowed to equal 0, or that you're not allowed to divide by 0, and you work it out from there using your math logic. Here we could do the same thing, but I'm, of course, going to go a little overboard. So a square root function. A square root function is a piece of a sideways parabola. Okay? On the side, I'm going to throw a little bit of work over here. Y equals the square root of x. Well, there once upon a time, I could square both sides. I'll have y squared is equal to x. When y squared equals x, when we did our unit on conic sections, we learned about this over here. Y squared equals x is really a sideways parabola, is what people like to call it. Although really parabolas can face any way they want. We're just accustomed to them opening upward or downward because we deal with functions a lot. Now, when we took the square root and we only did the positive square root instead of doing plus and minus, the positive and negative, that restricted us to only the top half of our square root function. If I had a minus in front, it would be the bottom half. So that's where this function comes from. Now there's a 2x plus 3 in here. If I rewrite this just a little bit, I will have f of x is equal to the square root of, I'm going to factor this 2 out, 2. When I factor out a 2, basically I'm using distributive property. I'm just doing it in reverse. We're accustomed to multiplying in. I'm going to divide out. If I divide that by 2, well, I'm left with x. If I divide that by 2, let's not get too crazy here. It's just 3 over 2. Now you can look at this as being the square root function, again, the top half of this sideways parabola, for lack of a better phrase. The 2 and the 3 halves each perform a transformation. This 2 over here, we consider this to be a horizontal compression. And it's a compression by really a factor of 1/2. And we had a long discussion about this when we were working with conics, and about how this behavior, even though it seems like a stretch because it's a 2, how and why it's a compression. So we did have a long talk about that, okay? Hopefully you remember. And then x plus 3 over 2, well, that's going to move our graph left 3 over 2. Left from where? Well, left from the origin. Okay? So my graph ends up being left 3 over 2, and it's compressed by a factor of 1/2. Well, what else does that do for us? So normally our square root function follows a special pattern. We go up 1 over 1. Up 1 over 1, 2, 3. Now I'm over 4, another perfect square. Up 1 over 1, 2, 3, 4, 5. The next one will be up 1 over 7, up 1 over 9. That's just the parent function shape. Now, when we have that 2 in there, which causes our compression by a factor of 1/2, it's a horizontal compression. So horizontally you're pushing in everything half as much. So I'm going to still go up 1. That's my vertical, but I'm going to go over a half. I'm still going to go up 1, but instead of over 3, I'm going to go up 1 over 1.5. Still up 1. Now instead of 5, I'm going to go up over 2.5. That makes it have this shape over here, and then we moved it over. So that's why it's a little bit bigger of a scoop there. When you take this compressed graph and you move it to the left 3 over 2 units, you end up with this graph. If you tried to tell the domain from the picture, which some people just try to do, from left to right, you're going to start here at negative 3 over 2, which is clearly included in your domain. It's defined at that point. If you plug it in, you'll get 0 under your radical, and you can take the square root of 0. It's 0. From there, it's good everywhere to the right, so that would make the domain from 0 until infinity, where 0 is included. Now, what else do we know? When you're finding the domain of the nth root of an expression, when n is an even number, so for example, we're given the nth root of something like this, your radicand, so this underneath is called a radicand. In the quadratic formula, we do refer to the radicand as the discriminant. That's a little bit more specific. The radicand must be greater than or equal to 0. So to solve algebraically on the side, if you were just trying to gather that information and do some work on the side, you would just take, in this case it's linear, so you can just take that linear expression, 2x plus 3, set it greater than or equal to 0 and solve for x. So 2x must be greater than or equal to negative 3, so x is greater than or equal to negative 3 over 2. If you need help visualizing it, I would sketch it out on a number line. This point right here would be 3 over 2, and greater than or equal, so this way to the right, which is clearly going to be like that bracket included notation until infinity. Okay, so that's another way to look at it. Oh, I'm doing 0. I don't know why I did 0 before. Sorry. Obviously, that's not right. It is that one. My bad. I was looking at that. I was supposed to be looking at that. So sorry. Now, what else can you look at in this case? There is some other information we can analyze. If you look at what you're taking the square root of, okay, you are taking the square root of a linear function. If we take that idea here underneath my square root, I'm going to draw a little graph. I'm taking the square root of this linear equation 2x plus 3. Well, here's 3, slope of 2, there's the line. I'm trying to take the square root of this linear function. When can I and when can I not take the square root of my linear function? My linear function f of x, or in this case it's side g of x, so it's the square root of g of x. My square root, I'm only allowed to take the square root of something when it's positive. I need to disregard this part that's below. How do you find where it crosses over from negative to positive? Well, who's the gatekeeper between negative and positive? The person holding guard of that spot is the x-intercept. How do you find an x-intercept? You set y equal to 0. Where's the y specifically in this case? Y equals 2x plus 3 is the linear equation we're looking at. If I set y equal to 0, 2x plus 3, you'll end up with x equals negative 3 over 2. That is where the entryway is, from negative to positive. And we can't take the square root of a negative, so that part's excluded. Only this part's included. You also know the end behavior of a linear function. And I know this is way extra, but this is going to help us with example 4 on this page. So your end behavior for this linear function is positive and to an odd power right there. So the end behavior is down and up. Also, that x value, it's an odd power, so it's cutting through the x-axis. It's passing through. It's not just turning around there. It's not just bouncing off of the x-axis like a parabola. So I will go from one to another. So I'm going from negative to positive, being that my end behavior is down and up. All right. Another domain, similar to 1 over x. This one just happens to be 1 over x plus 2. This has a transformation. 1 over x is the parent function. 1 over x plus 2, that just took the parent function, 1 over x, and moved it left 2 units. As it moves left 2 units, the vertical asymptote also moves left 2 units. You could think of it that way. So my vertical asymptote earlier, which was at the y-axis, is now here at negative 2. So if you know that that's where your vertical asymptote is, that means negative 2 is off limits. That means our domain goes from negative infinity till negative 2 union negative 2 until infinity. Another way to consider it is, again, You know your denominator can't be 0 because you're not allowed to divide by 0. So you take your denominator. You would use zero product property here. If this were x squared minus 4, you would have to factor first and set each linear factor separately to 0. Now, you could say set it equal to 0 and solve, or you could be a little bit more technically correct and set it not equal to 0 and solve. That means x is not able to equal negative 2. I really shouldn't have chosen green because that was my horizontal asymptote color. Sorry. So this over here also helps us get our domain. It gives us our restriction, the negative 2. Everything else is good. So my domain of the function is this right over here. And we're good. Our next example is similar to number 2. So I know I took a long time in the beginning ones, but it really is to prepare us for what is to come. Spend a little bit more invested time in the beginning, and you can spend a little less time later. Okay, so we're looking at this example over here. Now, earlier, we saw that we can label the inside of a radical as the radicand. Here we have a root or a radical symbol over the expression 10 minus x cubed. There's no index written inside that little hook of the root. That's an indivisible 2. It defaults to a square root. All right, we're there. My radicand is the expression. I put it in standard form. I even put in a placeholder. It's negative x cubed plus 0x minus x plus 10. Well, what are we going to do here? What was the rule? The rule is that your radicand, in order for our domain to be good to go, it has to be greater than or equal to 0. Well, what does that mean? I need to know where the gatekeepers are. I need to know when the radicand, which was negative x cubed minus x plus 10, equals 0. Why? To know where it can potentially cross. To know where the radicand can possibly switch from positive to negative or negative to positive. So positive to negative. That's the only way to know. All right. Well, how do I know when a polynomial, this is algebra 2 material right here, how do I know when a polynomial equals 0? Usually we just go for it. We factor. We factor, we use the zero product property, and we're good to go. Now, will factoring work on this particular polynomial? I mean, greatest common factor is out. We don't really have a greatest common factor unless you think of the negative. So no good there. Factoring by grouping isn't looking so great. It's not the sum and difference of two cubes. It's not the sum or difference of squares. It can't use quadratic formula. It's not a quadratic. Now, there are formulas that exist that we can use on cubics to solve them, but there's also just rational root theorem. Okay, rational root theorem. What are all the factors of 10 over all the factors of negative 1? And we're going to try those numbers using synthetic division to see which ones give us a remainder of 0. We can use the remainder theorem to speed up that process. The remainder theorem lets us know that we could just plug these in. If we get 0 there, they're also winners. Okay. We look at this. If I plug in 1, you'll have negative 1, and 10. That's not going to make 0. If I plug in negative 1, also not going to make 0. If you plug in 2, negative 8 minus 2 plus 10, winner. So 2 is going to work. Now I'm going to list out my coefficients. Negative 1, 0, negative 1, 10. I'm going to do the division and divide synthetically. Really, what am I dividing by? This right there means that you're dividing by the expression x minus 2. That is the factor. That is the box number right there, or the root, or the 0, but that is the factor. We bring down our first number, bottom times box, add them straight down, bottom times box, add them straight down, negative 10. And what's left? 0. That's my remainder. Other thing, box number comma box number is an ordered pair on that particular polynomial, this guy right up here that we were dividing. Now what's left? So I have that. Now I have negative 1 x squared minus 2x minus 5. That's a factor, and so was x minus 2. Can I factor that by hand? What multiplies to give me 5? That's to give me 2? Nothing. So this would require quadratic formula. However, if I'm going to get imaginary solutions, it's not really significant because I don't have any real zeros. That's the only place where it can change from positive to negative, and that's the only one I need to consider. So, what does this tell me? Quadratic formula, I'm going to start with just b squared minus 4ac. Again, a famous radicand. It's known as the discriminant. B squared is going to be 4 minus 4a, so negative 4, negative 1 is positive 4 times negative 5. So that's going to be minus, because it's a minus 4, a negative and a negative, minus 20, which means my discriminant is negative 16, which means it discriminates against real answers. So this is going to give me two imaginary or complex solutions. They always come in conjugate pairs anyway, when we have rational or integer coefficients. So no bueno, it doesn't help me out. So that means the only place where I can change from positive to negative, okay? The only place where you're going to switch from positive to negative is going to be at 2. Graphically, what does that tell me? Alright, so I'm taking the square root of some graph. Here's my x-axis, here's my y-axis, here's 2. I have some cubic polynomial. That means I could have pointing up, and there we go. So maybe something like this. What part can I take the square root of? Well, the part I can take the square root of, where is it? Over here, above the x-axis. So anywhere from negative infinity all the way until 2. And 2 is included so long as that square root is in the numerator. Okay? So which choice am I looking at over here? Looks like D is looking pretty good. Okay? So we have the first 4 examples done in sort of an extravagant, overboard fashion, but that's just what I like to do. Now that I've gone a little extra on those first examples, I'm just going to faster through these, but I'm still going to support some of it with graphs because I think having a great visual aid to assist your understanding here is going to prove to be really important. Now here again, I have the square root and even root of a linear. It's already a linear, but it is a polynomial. My radicand, my linear equation, must be greater than or equal to 0 in order for my domain to be in existence, for me to be able to take a square root. So you can just start off with 8 minus 4x must be greater than or equal to 0, which means negative 4x is greater than or equal to negative 8, which then also means that x is going to be less than or equal, I'm dividing by a negative 4, less than or equal to 2. Here's my number line to help me visualize. There's my 2. Here's my equal to, and then my less than goes this way. If you got something different, maybe reevaluate what you did. Maybe reread your choice the other way. If you had x on the right, read it from right to left. If you had this written, x and 2, don't read that as 2 is greater than or equal to x. That doesn't get you anywhere. You need to read this as x is less than or equal to 2. That makes more sense. Once you have it on a number line, it's a little easier to write your interval notation without any error. You're going from left to right. So negative infinity until 2. 2 is included. Throw a bracket on there, and we're good to go. So this right here is my domain. Okay? So finished, and it's also using interval notation. Again, to throw one little supplement on here, it's like I'm taking the square root of a linear function. The linear function that we are taking the square root of is the linear function y equals 8 minus 4x, which maybe when you were younger was more negative 4x plus 8. So here's 8, and we're playing equally right now, and the slope's negative 4, so right there. So I have that equation, y equals negative 4x, sorry, put the negative right there, y equals negative 4x plus 8. I'm only allowed to take the square root of something 0 or greater, so this is the part I'm looking at. Well, that means my x-intercept again was the gatekeeper. How do you get an x-intercept? You set y equal to 0. Every point on here is y value of 0, so 0 is equal to negative 4x plus 8. Bring the 4x over and divide by 4. Well, when x equals 2, we have our gatekeeper, our x-intercept, right there. 2 comma 0. Also our end behavior. I know my end behavior of this linear function. Also x was to the first, so I know it's cutting through the x-axis. If it were second, fourth, sixth power, it'd be a different case. Odd powers, we pass through the x-axis. Even powers, we're going to bounce off. And you'll see that around the factor itself. So even around this whole thing, it's to the first power. Okay, the degree, the multiplicity, different ways you could look at it. So I'm looking at this part, which is the exact same part in the number line, which is the same part I have written in my interval notation. All right, continuing. The main difference here is I'm taking the square root of another linear function. I could do this all over again, find my x-intercept. The main difference in this example, algebraically solving, is that the radicand 4 minus 2x must be strictly greater than 0. Okay? My denominator is not allowed to equal 0. this is combining with my radicand not being able to be negative. Therefore, my radicand expression must strictly be greater than 0. So then I'm going to do this one the other way, where I leave my constant here. I'm going to bring x on that side. 4 is greater than 2x, divide by x, and I'll get x is less than 2. Number line, how do I draw x is less than 2? Here's 2. Open circle, less than. We go that way. X is less than 2. So that's going to be, well, I don't know why I went right to the choices. Negative infinity until 2 with a parenthesis. So where's that? Negative infinity 2. There we go. Done. Next, an open-ended, same idea, not in a denominator. So 4 minus 3x is greater than or equal to 0. 4 is greater than or equal to 3x. That means 4/3 is greater than or equal to x, which also reads as x is less than or equal to 4/3. Number line, here's my 4/3. Fractions are our friends. Let's not use decimals, thanks. There's my 4/3. It could be included. And then we go this way right over here, and we're good to go. Maybe not my best shading job. Interval notation, negative infinity, comma, 4/3 with a bracket. Small, dinky bracket, sorry. What else can we talk about here? We could graph the actual polynomial here. Or not polynomial, I'm sorry. Graph the actual square root function. In this case, what will that look like? Well, I have the square root function. I'm going to turn it around. So I have the square root of negative 3x plus 4, which is the square root of negative 3x, dividing by the negative 3 to deal with distributive property here, minus 4/3, the negative on your square root function. Okay? Normally a square root function, I'm squeezing, it's something like this over here. Negative on the outside made it the bottom. It did a vertical reflection. It reflects it over the x-axis. A negative on the inside, however, will be a horizontal reflection. It's going to reflect it over the y-axis. So a horizontal reflection would result in something looking like this. The pattern mentioned before, up 1 over 1, up 1 over 3, up 1 over 5, will still hold true until this 3 is a compression of a third. Up 1 over a third. Up 1 over 3/3, also known as 1. Up 1 over 5/3, known as 1 and 2/3. So on and so forth. And it's also moved to the right 4/3. If that's moved to the right 4/3, makes no surprise to have your domain be what it is. Here we have a rational function, okay, a little bit more elaborate looking than the ones on the previous page. In order to do this, you say your denominator, which is x squared minus 9, essentially we want to know, when does it equal 0? Sort of like a trap, like, hey, when do you equal 0? Okay, you're not allowed. Really, you could also say when it doesn't equal 0. If you are going to bring over the 9, take the square root, not a big fan over here, okay, because you're likely to forget the plus minus, and we really should go about this factoring and using zero product property. It's going to get you more information. This is the difference of two squares. I could be a little extra here and look at it like this, right? Equal or not equal. How do you factor the difference of two squares? We use conjugates, x minus 3 and x plus 3. Equal to 0, or again, not equal to 0. First power, first power. This is important. This is going to be very important. That means we use zero product property. Zero product property. Okay? This is how you solve polynomials. You never bring another constant other than 0 to the other side and just factor out an x. That is bad. So this here, x can't equal 3, when I said that equals 0, or again, not equal, and this cannot equal negative 3. Now, just because x can't equal these two numbers doesn't mean it's for the same reasons. Your parents tell you, you can't hang out with that kid, and you can't hang out with that kid. You can't hang out with that kid because, I don't know, they get into trouble, and then you can't hang out with that kid because they don't like to do their math homework. Okay, well, they're both off limits for different reasons. The same could be true for x values. These x values in this rational function over here, maybe one is off limits because, limits, foreshadowing. Maybe one is off limits because there's an infinite discontinuity there. A vertical asymptote is known as an infinite discontinuity. Maybe the other one is off limits because there's a removable discontinuity there. A removable discontinuity can be removed from the function by reducing the rational expression by removing a common factor. Reducing, simplifying. If I try to look at this, can I remove either of them? Does the numerator factor to also have an x plus 3 or an x minus 3? What multiplies to 6, adds or subtracts to 3? Doesn't really look like anything. If it doesn't reduce, if it doesn't cancel, if you don't get 0 over 0, if I plug in 3, 9 plus 9 minus 6, does that give you 0? Absolutely not. How about here? 9 minus 9 minus 6 still doesn't give me 0. Okay? So these are both infinite discontinuities. They're infinitely there. They're stuck. You can't get rid of them. They are non-removable. Okay? So they're both infinite discontinuities. They're also known as non-removable. Alright, this next example I accidentally did off the camera, so I apologize, but I think you have the hang of this type right here. Next one over here. You should be fine. This one over here, again, I don't care if it's removable or non-removable, because the directions are just asking your domain. So x squared minus 4 is just not allowed to equal 0. That's the only restriction we have going on. Factor x plus 2 and x minus 2, because it's the difference of two squares, so I'm using conjugates. X plus 2 then is not allowed to equal 0, and x minus 2 is also not allowed to equal 0. Therefore, x can't equal negative 2, and x can't equal 2. Alright, what does that make our domain? Everything except those two numbers, which is indicated by the interval notation in choice B. And same idea here. I have a denominator of x plus 2, which is not allowed to equal 0. X then is not allowed to equal negative 2. That would just be, this time, not interval notation. Looks like it's represented this way. That's it. Here, there's a comma. These look like ordered pairs. I have seen some textbooks use commas for interval notation, though. And they use that to separate two intervals. But that wouldn't make any sense because it's not in order from least to greatest from left to right. So that would be silly. I have two vertical asymptotes drawn in this picture. I don't know exactly where they are, though. It is asking us for the domain again. Same rules apply for our domain. Our domain is still that this quadratic, x squared minus 2x minus 2, is still not allowed to equal 0, so I need to find out when it does equal 0. So I know which x values are not allowed. So how do I find out when this equals 0? I want to factor, but it's not factorable. If you can't factor, good old quadratic formula. So negative b plus minus square root of. B squared is 4 minus 4ac, 1 times negative 2, all over 2 times a. 2 plus or minus the square root of, that's plus 8. 4 plus 8 is 12, all over 2. So again, x can't equal. Carry on with this. 12 is 4 times 3, right? The square root of 4 times 3 is really the same as the square root of 4 times the square root of 3, which is the same as 2 square root 3. Therefore, 2 plus minus 2 square root of 3 over 2. We can reduce this using what I like to call the pretzel. So we have this and this. And where does that get us? A 2 reduces from everybody, right? So 1 plus minus square root of 3. Well, who's bigger? 1 plus square root of 3 or 1 minus? I'm going to put money on the fact that 1 plus the square root of 3 is the bigger one, right? And over here, that one will be showcasing the 1 minus square root of 3. So my domain, you don't need a calculator. You're going to write negative infinity. Maybe I should label what I'm doing. So my domain is negative infinity, comma. My smaller number was 1 minus the square root of 3. It's not included, using a parenthesis. Union, everything in between. 1 minus radical 3, comma, 1 plus radical 3, parentheses, union, pick it up from there, 1 plus the square root of 3, comma, infinity. And we're good to go. No calculators needed, no Desmos needed, no iPhone calculator, no graphing calculator, nothing. Okay? That was absolutely everything.
This next example, I gave you quite a bit of work on stuff like this during our chapter of conic sections, and then after that our unit where we were just graphing essentially everything you've ever learned to graph. That may or may not be a comma in between. That might just be a spec from the copy machine, which I also mentioned earlier. They like to do that. Now, without this picture, how would you know what this graph looks like? I'm telling you right now, I promise this is not equal to the square root of 3 minus x. Do not do that, okay? Absolutely not. No. That is very bad, okay? That is not good. Please never, ever, ever, ever do that. That is bad. What can you do? If you weren't sure what the graph looked like, okay, keep this in mind, bury it in your brain, somewhere where you could easily access it. I have right now y equals the square root of 9 minus x squared. If you have a unit of conic sections under your belt, if I square both sides, I get y squared equals 9 minus x squared. I'm going to bring over add x squared. X squared plus y squared is 9, also easily referred to as 3 squared. What is this? That is a circle. That is the equation of a circle. You may have done it in geometry, you may have done it in algebra 2. The center is at the origin 0, 0. The radius is r equals 3. The equation of a circle is x minus h squared plus y minus k squared equals r squared. Am I on camera? No. Sorry, I'm just adjusting a bit. Sorry. So, there we go. That's the equation of a circle. However, how is this presented to us? It was presented as a function. If it's presented as a function, it passes the vertical line test. Any other circle would normally not. That's because this one, right here, is a special kind of circle. And what kind of circle would that be? That special kind of circle is just a semicircle. It is only the top in this case. So the radius is still 3, 3, 3. The center is still 0. So what is the range? Now we switched it up. What is the range of the function? Well, the range always goes from the bottom to the top. So the lowest is 0, it's included. The highest, it goes as 3, which is also included. Range, right there. Done. Alright? Next, this one just to do quickly. This is also absolute value of x plus 3. Absolute value of x plus 3 is really a transformation of the parent function y equals absolute value of x. Many of you memorized that the absolute value of x is a v. That's true. It is a V shape, but of course, what am I going to do? I'm going to over-explain something right now, because that's what I do. So, if you look at it this way, and you think of it as the V is the parent function, the x plus 3 moves the graph 3 units, I don't know why that didn't focus, 3 units to the left, the slope of the branches, why? There we go. Move to the left 3 units, that's right there. It's negative 3, 0, my vertex, and then the slope here is up 1 over 1, up 1 over 1. If you had graph paper, that could work out nicely for you. Another way to look at it though, okay? Of course, it's graphically. What if I just graphed the line y equals x plus 3? 1, 2, 3. Slopes 1. 1, 1, 1, 1, 1, 1 is the same as up 10 over 10, or down 3 over 3. Down 3 over 3. So I could carry on like that. There we go. Okay, so I have this guy right over here. Then, out of nowhere, something comes along and they're like, no, we're going to take the absolute value. What does absolute value mean? Distance from 0. Distance is always positive. So essentially we're going to take any part of our graph that's not positive, and like a mirror, we're just going to find its reflection. Instead of this being down 1 unit, well now it's up 1 unit. Down 2, well now it's up 2. Down 3, now it's up 3. And so on and so forth. So this is no longer in existence. That is gone. And thus the V-shaped graph is born. Alright? Does this graph depict a function of x? Absolutely not. Why not? It super fails the vertical line test. No good. We even have 2 y-intercepts. That's failing the vertical line test right there. So y is a function of x? No. Y is not a function of x? Correct. It's not a function of x. Just means it's not a function such that x is my input, y is my output. That's what this statement means. My output is right there. My input is right there.
In which of the following equations is y a function of x? It shouldn't take you that long to look at this and know that this is clearly a linear function. If this takes you any more than a half of a second, you have some work to do, okay? You are struggling, okay? That is a linear, so that is definitely a function of x. So that means that choice D is out. That doesn't mean A is the answer. It means that's out. So it's either A and B or just A, so none of these is also out. Now this looks a little messy, but how can I make it more familiar? Granted, I can kind of look at this and just know it's going to be a function. Okay, the answer is going to be C. But let's help you out over here. What can we pay attention to? Maybe what we could do is let's bring everything that has a y in it to the right side. I'm going to solve for y right now. So x is going to be alone. I'm going to have 4y minus 2x squared y. I'm trying to solve for y. You should be a seasoned math student. You should not be giving off any rookie tendencies here. Factor out the y. If you didn't know that, you do now, okay? 4 minus 2x squared, close that parenthesis. Then I need to get y by itself so I can look at it and see if it's familiar to me from algebra. So I'll have y equals an x in the numerator, and I'll have 4 minus 2x squared in my denominator. Polynomial top, polynomial bottom. This looks like any other run-of-the-mill rational function that we did in Algebra 2 when we were dealing with our functions, okay? So yes, it's both a and b. This one is a function, and that one is a function as well. Same idea here, clearly linear, that's in, okay? Both a and b or both a and c. Okay, here, y equals 7 over 2x squared. Well, what does 1 over x squared look like? You remember, 1 over x squared kind of looks like a volcano, okay? This is y equals 1 over x squared. A couple other things to point out. My denominator can't equal 0, just like we mentioned before. When will the denominator equal 0? When x equals 0. So that means I have a vertical asymptote or an infinite discontinuity over here at the line x equals 0. Okay, my end behavior, if I plug in infinity, the limit at infinity, as x gets larger and larger and larger, what happens to my rational expression here? Well, it gets smaller, it's approaching 0, and it'll never hit 0. Same idea here, because you're squaring, so if you plug in an input, if you plug in a negative or a positive in for x, you'll have the same results. This is actually also called an even function over here. That rule was f of x will equal the f of negative x. That's what makes something even. Alright, now the squared. This is really an x plus 0 to the second power. An even power, if you look against this asymptote, both of my branches are pointing in the same direction. So once you know where one is, you can easily figure out where the other one is. Alright, so that's why I want to go over this quickly. So is this guy a function over here? You betcha. Now what about this? You should be able to look at this and know that this is an ellipse. Okay, you have x squared and y squared, which gives off conic section clues. It could be a circle, ellipse, hyperbola. It's not a parabola because only one of the variables here is being squared. If I get this equal to 1, which is what we did with conics, you'll have x squared over 7 plus, I'm going to rewrite this as y squared over 7/3, because we don't want to leave that 3 up there, equals 1. I could even rewrite it as those things under a square root squared, under a square root squared, so I even know how far out I have to go for my major and my minor axis. This is definitely an ellipse. And one thing I could tell you about ellipse, an ellipse is definitely not a function. So you're out. Okay? So what's the answer? A and C. So right there. E will be your final answer for that one. A is good, C is good, E is your answer. Alright? If you solved for y, y would be the cube root of x. Is that a function? You're on your own, okay? Here, if I try to solve for y a little bit, let's clean it up. I'm going to get 2x plus x squared when I multiply that 2 plus x over, and that is equal to 2y squared. I'm going to clean it up a little more. I'm going to have x squared plus 2x minus 2y squared equals 0. Telling you this is a hyperbola. If you had to do more work with it, I would complete the square on this. You don't need to here because technically it's already a completed square. We don't have a linear term. So I'm going to add 1 in here plus 1, which means I have to add 1 to that side. I factor this, x plus 1 squared minus y squared. I'm going to divide out that 2 in a second. Well, not divide, but you'll see. Well, yes. Equals 1. That's good. We want that 1. But multiplying by 2 is the same as dividing by 1/2. You could either put a 1/2 down in that denominator. Oops, sorry. You could either put a 1/2 down in that denominator, or you could even write that as the square root of 2 over 2, which I promise is the square root of 1/2 squared. But either way, it's a hyperbola. Whatever way a hyperbola is going, whether it's horizontal, vertical, slanted, there's one example. Maybe over here I could draw a little sketch of another. If it's a hyperbola, it's not a function. Okay? Not really a very beautiful graph there, but hyperbola nonetheless. Okay? Here you are given a function. It's important that if you're scared and confused because you see something unfamiliar, that you just analyze what you have and what is being expected of you. You're given a function f of x. F of x is just a cubic polynomial nothing to get alarmed over. And all they're asking us to do is deal with this composite, this composition of functions. While x plus delta x isn't really a function, as far as we know, it is an expression that is going to be very, very, very significant in calculus. Delta x treat as one unit, okay? It's not triangle times x, okay? It's its own new letter in the alphabet, x, y, z, delta x. Delta is the Greek letter. It means the change in, all right? If I'm looking for that, f of x equals 2x cubed plus 3x plus 1. Well, what is our new x? Our new x is x plus delta x. And where is that going to go? Everywhere there's an x. Okay? There's a reason we reviewed Pascal's triangle. It's just going to make your life a lot easier. Please do not be the person multiplying x plus delta x 3 times. You should have a pretty strong understanding that this is going to be row 3 in the triangle. We're going to use 1, 3, 3, 1, and x to the third, x to the 2, x to the 1, and then none, and then backwards, delta x to the 3, to the 2, to the 1, and then none, and distribute the 2. You should be able to do this the way I'm about to do it, all in one shot. So 2, x to the third, plus 6, x to the second, delta x, plus 6, x, delta x to the second, plus 2, delta x to the third. Distributing some more, plus 3x plus, running out of room, 3 delta x plus 1. That's it. You're done. Where is that? Right there. Alright. Here I have a slightly different example. I am given a function. This one's just called g of x, not a big deal. And they don't just want me to find the g of x plus delta x. Do not think that this is more than what it is. You're going to do what we did in that last example. We're just going to evaluate it for x plus delta x minus the original g of x function, and then all over delta x. Here's a piece of advice. Your entire g of x is going to somehow cancel out. Okay, it's going to all cancel out there. And then this delta x, it is going to reduce out. Alright, promise you that. So, what are we going to focus on? A couple things. I'm going to do a little color coordinating after, of course. And I also want you to think of this little delta x right down here. I'm coloring it purple on purpose. Alright, that's our, on the emoji keyboard, you know that little purple devil guy? That's him, okay? He's going to have to go eventually. He's no good. He's a bad guy. Causes us some troubles. Not always bad. He has a big job to do, but a little bit bad. Okay, a couple things. That's g of x. Where do I need g of x? Well, it's in blue. G of x will be right there. In orange over here, I'm going to find the g of x plus delta x. I'm going to find it. Some of you will hopefully be able to do this all in one big step. I have confidence in you. But I'm showing the work right now. Again, Pascal's triangle, you can use that again, 1, 2, 1. Distribute the 3. So orange is that right over there. Okay, now that I have everything figured out, I'm going to go for it. I'm going to squeeze it kind of up here, okay? So that means I start off with x squared plus 2x delta x plus delta x squared plus 3x plus 3 delta x minus 1. There's my orange. Next, I'm going to switch to a darker color for a second. Minus, really you would need parentheses here, okay? I'm going to write them for right now, and then I'm going to distribute without writing a new line, okay? I'm just going to sort of do it in my head. Scooch this over a bit. So in here, x squared plus 3x minus 1 all over delta x, which is our little bad guy, our purple emoji, little devil, our delta x. Okay, So what from the numerator, without rewriting this whole thing, okay, let's not go crazy here, what from the numerator is going to clean up? X squared and x squared, 3x, because it will be negative, see? 3x, 1, because it will be positive, and 1. Now look at what is left. You're left with 2x delta x plus delta x squared plus 3 delta x all over delta x. What do these all have in common? They all have a delta x. So that's gone. One of those is gone. That's gone. That's gone. Normally I would write this out and show it a little bit better, but space is limited right now. What's left? 2x plus delta x plus 3. Please don't do it the way I just did it. I am setting a terrible example. Please use a piece of notebook paper or write it out a little bit better, or maybe don't be so wasteful with space like I was. All right, a little reckless. This was not really necessary. I could have just gone right there. But yeah, your answer's right there in the box. That is all there is to it. Okay? Don't overanalyze it. Here it's the same idea, except instead of using delta x, they're using h. Books go back and forth. Delta x and h are really going to be representative of the same thing in the future. Here they're asking us for composite functions, to plug one function into another. G of x is your outside function. Everywhere inside the x, so now it's g of blank equals blank plus 5 over 3. And what's being plugged into g? Well, this right over here. On this side of the equal side, I'm plopping in that f of x. On the other side of the equal sign, everywhere I have an x, I'll fill in x minus 2, and you go from there. So that real style of doing it is really all you do for composite functions. Here you're just working backwards. They're asking you what built this function, okay? I'm not going to finish this. You clean that up. Here, this is not the same notation, all right? That is not equal to f of g of x. That is not what that says, okay? What this says actually is f of x times g of x. They're just saying find those two functions and multiply them. They're both binomials, so you're going to multiply. You can use first, outer, inner, last to get that all done, but it is not that. It is multiplication. Okay? Same idea, but next case, this is division. Okay? This is equal to f of x over g of x. Right? If you can factor, solve, clean it up a little bit, go for it. Keep your domain in mind, but definitely go for it. The examples are asking about something being one-to-one. They're asking about inverses. I know it's been a while, but not that long of a while, because we talked about one-to-one in our trigonometry unit when we did trig inverse. One-to-one means it passes the vertical and horizontal line tests, that it would be a function in this direction as well as in this direction. Is this function one-to-one? Does this function pass the horizontal and vertical line test? Well, this function is merely a transformation of 1 over x. The 7 is just a vertical stretch of 7, so this would just be really stretched. I'm sorry, I could pull this down a little. That would just be stretched vertically, and the plus 2, it just moved it left 2. So it's definitely one-to-one. So yes, it is. If it is, find its inverse. How do you find an inverse algebraically? First, you switch x and y, and then algebraically solve for y. This is representative of y. So if I switch them, I'll get x equals 7 over y plus 2. I gotta solve for y. Back to basics, okay? Don't be a weirdo. Don't do anything strange. You're going to multiply the y plus 2 over. What does that get for us? That gets us, I'm just going to draw an arrow because I can't really go this way. X, I'm distributing the x. xy plus 2x is equal to 7. Subtracting the 2x. xy equals 7 minus, no, it's not a minus sign, 7 minus 2x. And then, in the next step, I'm just going to divide by x. So 7 minus 2x over x, right there. That's just notation for inverse, okay? So that means f inverse of x. It does not mean 1 over f of x. Context clues, okay? F of x equals this parabola for x is greater than or equal to 0. What the heck are they talking about here? You have a parabola with a vertical stretch of 2, shifted up 1 unit. There's my vertex, up 1 unit, And then instead of over 1 up 1, it's going to be over 1 up 2. And then instead of over 1 up 3, it's going to be over 1 up 1, 2, 3, 4, 5, 6. Everything vertically is stretched by 2. Okay? But what is that? X is greater than or equal to 0. Well, here's 0 on the x-axis, and x is greater than or equal to it. That means we're only dealing with this side of the parabola. Okay? The highlighted part is the only part you are dealing with. That means, no, this is gone. You got rid of it. Now it's 1 to 1. That's why they do that. So, maybe in yellow, this right here is our domain, which will become the new range. Okay? To find the inverse, you're just going to work it out like normal. If you think about it, this is the positive half of the parabola, so that means you'll have the positive half of the square root. So when you do the work, you're going to end up with the square root. The positive half is the yellow side, and then the negative is the green side. And we're not going to have this. Nope. Not at all. Alright, so keep that in mind when you're finding your inverse function. The last thing I want to say is when you get a function like this, please don't be a weirdo and tell me you don't know what that is. Okay, it's a linear function, I promise. My slope is 2/3 and my y-intercept is 1/3. It is not anything crazy. But one too many people tell me that they don't know what this thing is. So please don't be that person, and I hope you're able to figure out the examples in this section of the packet.